Hello, and today we are going to be installing Zephyr with a Nordic NRF52DK. This is specifically a NRF52833 as the chipset. So let's start the install. Okay, so first thing you want to do is go to your web browser. I'm going to be installing this on Linux since it's the easier option. You can do this on Windows, but I have a preference to do this on Linux. Usually I work it in a Docker container and not on a virtual machine, but for ease sake we're going to do it on a virtual machine. So first we want to look up Zephyr and getting started. So here is the getting started guide from the documentation. So I'm not going to be using the Nordic setup. I'm going to install the full Zephyr operating system and compiling for it. So we got our getting started guide here from the documentation. So this is for 3701 release candidate. So we simply have our instructions over here. We open a terminal and then we can start copying these instructions and just pasting it into a terminal. Just give our password. Okay, so we're done installing now the upgrades. Then our dependencies are going to be CMake, Python, and the device tree compiler. So CMake is your makefile generator. Python is for some of the scripts that they run, and then the device tree compiler basically translates a device tree file into a binary file for you. So on the next step, we have, if we're using an Ubuntu version older than 2204, we need to add the following. But for mine, which is host name control, if I can spell it correctly, even helps you. How nice, that's new. Then we can see here I'm on Ubuntu 2024.0 LTS, which is a version higher than 22.04. So we can skip this first step. Then we got everything that we need to install. We just copy that over and then paste it into a terminal. And I'm going to add a -y to that. And then it's going to install all our dependencies. I'd actually suggest you grab a cup of coffee because this takes a while. I'm going to skip ahead, obviously, with editing magic, but some of these steps, if you're doing it on your own, you're in for about an hour, maybe 2 hours. Okay, so all our packages are installed now. Now we can just check that everything that we need has installed correctly. So we just copy the CMake version. Okay, so that just confirms that everything is installed. Okay, we can see CMake version, that's correct. Python version, and then the device tree compiler also here. So we go to the next step. So the next step is going to be setting up a Python virtual environment. So we need to install the package for that. Then we need to create the virtual environment. So I'm going to create it in the same place as what Zephyr makes it. So I'm going to be installing it in the same place as what Zephyr suggests. So pwm pwd. So that is my home folder. So home Bucky. Okay, so we create this virtual machine. Okay, then we say ls. And we can see our virtual environment is over here. So that's a new folder that's been created. I'm going to go into a separate terminal, pwd that. So still in our home folder, and then I'm going to say ls-a, so list all files. Now the file that we're looking for is this .bashrc folder. So this determines what commands run every time you open a terminal. So on this next one, if we copy this command, source Zephyr environment, this will activate your Python environment. So if you paste that in, you can see we added an env. So this indicates that you're in a Python environment. So I wanted permanently for every terminal that I open that we are now in a Python environment. So if we say cat current directory .bashrc, you can see at the end of the file there is nothing currently. So what we want to do is we want to say echo quotation mark dot instead of source, and then we want copy this part of the line, so part that activates the Python virtual environment, and then close your quotation mark, double arrow to the right hand side, and then we want to put that in our .bashrc file. So this double arrow will append the output of the command to this file. Okay, then then we run a cat command again. And now you can see at the end of the file, it added this command to the bash script. So if I open a new terminal now, it automatically activates the environment for me. So I don't need to run this source command every time I want to activate the environment. This is dependent on your preferences. This machine will basically only be a Zephyr compile box at the end of the day. Okay, so the next thing you want to do is you want to install West to the specific virtual environment. You have to make sure that you have got this .env in the front, otherwise you're going to install it on your global Python interpreter instead of your Python environment. So we just say yes, and this is going to take a while again, I believe. Okay, that didn't take too long. So the next thing you want to do is we want to initialize our West installation. After we have initialized West, the following thing we want to do is we want to update our West. So we can just cd into the Zephyr project and then we say West update, if I can spell it correctly. Okay, so now we're running the update. I'll get back to you when the update's done. Okay, so roughly 2 millennia later, we are updated. So we can continue now. West export. So we want to export this link set that CMake can use West, or at least build the make files for it. Okay, we can see Zephyr yada 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 has been added to the user package registry in .CMake. So we got that added successfully. Now the following one is going to be a bunch of requirements for Python. So the Python dependencies, so that will just pull everything from pip. So we just install that again. Okay, so we got all the Python dependencies installed now. Now we're going to actually add the SDK. So we are going to be installing this particular one. Okay, so a few things here. Depending on which platform you are on, you can alter the URL to what your platform is compatible with. But I'm on Ubuntu and on an x86 platform, so I don't need to change anything over here. I'm going to copy this download command. So this is two commands. The one is to download the tar file and the other one is to verify the tar file itself. So we just run that. So two vgets, one gets the tar file, other one validates that you got the correct tar file. Okay, so we start that download and this will take around 5 minutes. So I'll be back when we're done. Oh, small little change. It wants you to, well, the instructions want you to install it in your home folder. I'm not installing it in the home folder. I'm installing it in the Zephyr projects folder. That's the only real difference here that I have. So I'll get back to you when it's done downloading. So we're done downloading the package. What you want at the end of the day is this out that it says OK over here. That means your file has downloaded successfully. And we can see it over here. Here's the package. Now the next command is to untar the file. So if you're coming from Windows, this is like unzipping a file. Then we start the unzip process. And this takes a while again, so I'll get back to you when the unzipping is done. Okay, we're done extracting the file. We can ls. Now we can see that there is a Zephyr SDK folder. Unfortunately, this background doesn't do much justice for folders. But anyways, so we can remove the Zephyr-SDK_Linux. So we're removing that file. Free up some disk space. Okay, now we want to run the setup script for Zephyr. So we cd into Zephyr-SDK and we run the setup script. Yes, we want to install the host tools and we want to register Zephyr SDK CMake package. Okay, so the script will now run. Script is done running. So next we want to add some UDEV rules so that we can flash boards without being the root user. Copy this command. I need to alter this command because my stuff is not in the same location as what the SDK says. So we say Zephyr project looks correct. Let me just expand this. Yeah, that looks correct. To add the password for this. Okay, so we got the UDEV rules installed. I don't really use them, but you might. Okay, next we want to test our installation. So we want to go into our Zephyr project. So I'm going back one directory, ls, then we can see Zephyr is here. We can go into it, ls, and we have a bunch of folders here. We want the project folder, but before we do that, we're going to open a new terminal, we ls, then we see this boards folder. So this contains all the MCUs and examples for creating boards. So here is all the supported brands for Zephyr. Then what we want to do is we want to cd into Nordic, since I'm using a Nordic board. Then here is all the supported Nordic boards. I want the NRF52833DK, so we say NRF52833DK and then ls. So here's a bunch of configuration files for it. The one we want as our board is this one. So this is the device tree file for it. So we copy our west build command over here, paste that, and then what we want to do is replace this board name. So I'm pressing home on my keyboard to go to the start of the line, and we delete the board name and we simply paste it. Oh no, that didn't work as intended. We try again, copy the command, paste it, press home, delete the your board name part. Now we copy this DTS file's name, so only the name of the file, not the .dts. So this is the board that we'll be using, and we add that instead of the your board name, and then we build it. So if you get a output that looks like this, which has the memory regions, then you have successfully built your application. All right, so we press ls again. You will see it created a build folder. So if we cd into the build folder and ls, we'll have all these files. Your output will be in the Zephyr folder. So cd Zephyr, and then we ls again there. So your output files are going to be this Zephyr hex, the Zephyr bin, and then somewhere here is an elf. There we go. There's the Zephyr elf. Okay, so that's the output. So you've successfully built. So we go back. Okay, now we need to be able to flash our board. So we're going to need the Seger JLink tools. So we say Seger JLink tools. So what you're looking for is this JLink that /JTrace downloads for Seger on seger.com. Okay, now depending on your platform that you're on, you want to download accordingly. So for Linux, and I am on a Debian install, I'll be downloading the 64-deb installer. If you're on Windows ARM, you install, you get that installer, Windows, etc., etc. If you're on something like Red Hat, you want RPM installer. So, but anyways, I'm getting the 64-deb installer. I want to download it, find my life away to the terms of use, and we download the software. Okay, and while we're at it, we are going to get VSCode as well. Just go to the download sections for VS Code. Okay, I'm on Ubuntu, so I'm getting the .deb file. So any Debian based should work with this .deb. So we download that. Just wait and make sure. Okay, it started to download. Okay, then we can close that tab because it's heavy on my CPU. Okay, so we open a new terminal. We go to our home folder, ls, and now we're gonna go to the default downloads location. So cd downloads. Okay, now that we're in the downloads folder, you can see there are two .deb files. So we're going to say sudo apt install and then // so your current directory, and then we want to install the JLink deb. Need to give it the admin password. Okay, downloads are performed. Unpacking, so seems to work. Let's just double check. Okay, we got the JLink software installed. Next one, we want to install code. So it was basically the same command if that was too fast. So here's the command itself. It's stuff. Now we got these two files to free up some hard drive space. I'm going to delete them with RM and RM JLink deb. Okay. So there's no folder in here. So the command for code, for VS Code, will be just code. You enter that, we check that. Okay, VS Code launches. Okay, excellent. Okay, we are mostly done with Firefox. So I'm going to close that, and we're going to do 90% of this from the terminal. Okay. Sega J-Link documentation is absolutely bloody abysmal for Ubuntu. So to find all the commands that you can use for a Sega J-Link, we are going to go ls/user and then bin. This might differ on your particular operating system. And we're going to say ls user bin J star. So list everything that starts with a capital J in this particular folder. Now, here you can see all the J-Link utilities. So the particular ones we are interested in is JFlash Lite. That is a graphical interface to flash your MCU. So the other one is the GDB server. This is one you might want to use if you're using remote debugging. VS Code will auto launch this for us. First, I need to mount the J-Link itself. Okay, so you can see here the J-Link that I supply on the DKs is a Sega J-Link OB, which comes up as a flash drive. You can open it. And you can see here Sega J-Link. I've not been able to get it to the drag and drop to work on Linux itself. I don't know if it's the VM itself, but I can't get drag and drop to work. It says this flash drive is read only. But we can get around that by using JFlash Lite. So we just copy that name and paste it in our terminal. Okay, that will launch the graphical user interface. So JFlash Lite is a development tool not designed to be used for production purposes. Okay, that's fine. So this is the interface. We want to click over here. We want to say NRF52 and 52833. So that's only the one currently. It might be different on new versions. Then we just click OK here. Okay, our interface is going to be SWD and at 400 kilohertz. So great stuff. Now let's bring up the board itself. You can see at the moment the board is blinking. This is from prior stuff. By default, these come with a slow pulse PWM. Okay, so first thing we're going to do is erase the chip. Okay, erasing is done. You can see the blinking has stopped. Then you want to add a bin file. So we're going to navigate to our Zephyr project where we did our build. So we go into Zephyr and then we go to our builds folder, Zephyr again, and then we want our bin file. We open that file and then we say program device. Then you'll see as soon as the programming is done that the board will start blinking again. And you can actually see now that there's a different LED that's blinking. Okay, so we have now proven our build system does indeed work. Okay, so next thing we're going to do is we're going to open a new terminal. We're going to cd to our home directory, and then we're going to mkdir, so make directory. I'm going to make it source. ls, you can see the source folder is created here. We cd into source. And by the way, if you're wondering how I'm auto-completing this, it is with pressing tab. So starting letters, press tab, it will auto-complete. Next, we want to copy the Blink example to our source folder. So we're extracting the Blink folder from the SDK itself. So we have a separation of concern when it comes to the SDK. So I'm not building inside the SDK. Completely separate, isolated environment. So what we want to do is we want to find the Blink example, which will be in our Zephyr project, Zephyr, and then samples, basic, and then there's Blinky over here. So copy, home directory, Zephyr project, Zephyr again, Zephyr, samples, and then basic, and then Blink. Actually, no, we don't want to CD. You want to CP and then go back to the end. So first one is source with copy and the last one is destination. And we want to do Blink. And then we want to go to our front again and we want to copy recursively. So copy everything that is in this folder to the current directory we're in and name the folder Blink. Okay. If we run ls, we can see there is Blink. ls Okay, then you can see here, over here is Blink. If we go to the Zephyr project, samples, basic, and then Blink, you can see the files match up. You can see even in source, we'll have ls src. You can see cmain is also there. And then if we look in samples itself, there is a ton of stuff in here, even for the Bluetooth. Hordes and hordes and hordes and stuff for the Bluetooth. All sorts of examples here for you. Now that we're in the Blink folder, we just open this folder in VSCode. So code dot. Yes. And then source is main. So this is the basic Blinky example. I'm not going to go over it. Mostly very, very simple Blinky application. Now here it determines from the device tree which LED it's using. One adjustment I'm going to be making is the project conf, and all I'm going to do there is change the compiler optimization to debugging. By default it will compile as, I believe, as release. I'm not too sure on that one. Now in here I'm going to create a script file which is going to be build.sh, right? And then inside this build folder I'm going to say mkdir-p, so ignore if existing and make a build folder. We're going to cd into that build folder, and then we are going to run cmake, going to pass it a few parameters. So dboard, so we're telling it which board we're compiling for, and then we need to get our Zephyr base directory, so that will be this defined, so Zephyr base. Now we need to find our directory, okay, and then we say cd Zephyr project and cd Zephyr ls. Okay, so this is where our Zephyr project is located, and then we say pwd, then we copy this path that it just output and paste that in, and then we do 2 dots back, so 1 directory back. Then we run the following command, which is make-j, so j will take up all the threads. Okay, so to test this command, we create a new terminal, we delete the previous one, and we say test this, we say bash build.sh. It will help if I actually implement some settings, so I'm just going to do that quickly. Settings, we say autosave on, we want it after delay. This is my preference. I like having autosave, but usually I have a Git repository behind me, so I can roll back anytime I want. Let's try building this. Okay, so if you start seeing an output like this, you're basically successfully building the project. So at the end of the day, you want to see an output like this, and then the elf. So you can see here in your build folder in Zephyr itself that you have your build output over here. So next thing on the agenda, we want to install a few extensions for VSCode. So this is going to be C. So we're installing the C package. Then we want Cortex. And we want this extension for Cortex Debug. This is specific for ARM. If you are going to use another platform, you'll have to find your own debugger essentially, but this is the ARM debugger for VS Code. So if you scroll down on this, you'll see a link eventually where it says usage, where if you open this link, then you can see here's all the configurations for this plugin. All of it. And I mean all of it. This has been one of the most easiest extensions to work with. And we go to our debug tab and we say create JSON file. And we want to use the Cortex debug as our base file. When it starts up, it gives you this base folder. Already sets it up as your server type as JLink. It supports a myriad of server types. So we need to add a few options here though. We want to say device is a NRF52833. So we're specifying what we're debugging. Our interface is going to be SWD. Can use the defaults as is. Then we set the GDB path. So this is the tricky one. So we're going back to our terminal again, just to find this particular file. We're going to cd back to our user folder and then into the Zephyr project, cd, and then we are going into the SDK itself. Then you'll see in the SDK, there's a ARM folder. You've basically installed every single compiler under the sun that this thing supports with the method that I'm using. So we want to look at the ARM compiler. So we go ARM EBI and then ls, and then we're going to go into the bin folder And then all your ARM tools are here. So your compilers, all of it. So here's your C compiler, here's your C++ compiler, adder to line is here as well. Basically anything you need. So what we're looking for is the GDB client, which is this one. So we pwd this. So we copy this path and paste that into our path for the GDB path. So we get the Zephyr GDB as well here. Okay. And then optionally you can specify the RTOS, and that's going to be capital Z, Zephyr. So that should be all of it. We need to add the elf. The elf will be in your build output, Zephyr, and then you want your Zephyr elf, which is this one. We just want to copy the relative path to it. Okay, close the bracket, want to add it in front, and we want to give it the absolute path as our workspace folder. So now we've got our Zephyr elf linked up, and I believe the only thing we need to do is we need to configure a task. So F1, and we say task, configure a task, create a task from a template, yes, and we say others. Okay, so this is going to be our build task, type command. This is going to be that same command that we used to build it. So this is going to be bash build.sh, and then a small little addition to this is going to be problem matcher. We're just going to set that to nothing, an array of nothing. So if we go press F1 and we say run task, run task, you should see a build over here. So a label is the name, and this is the commands that will run. So you just want to say run the build command, check that it works. Yeah, seems like it's working. Great stuff. Then we want to go back to our launch, and then we want to add a pre-launch task, and that's going to be build. So this will run before the debugger starts, so it will build your application automatically. Okay, one more configuration file. Then we want our C++ edit configuration JSON. Okay, so we go back to our previous terminal where all of these were, and our compiler path is going to be this path again. And then /, then we want the ARM GCC compiler, which is this one. Okay, it's going to pop up this. Then we go back to our terminals. Final thing that we want to add is the include folders. So we just need to copy the Zephyr project path. So wherever you installed the Zephyr project, then you want to / and $. So that will recursively include all the files in the IntelliSense. You can see here at the bottom, let me just open a C file. You can see here at the bottom that the IntelliSense is updating. So this is how you, that's how you add everything. Okay, so the VSCode project is configured, which is brilliant. Now you can see in our debug tab, so either you can press F5 or you can start the debugger from here. I'm going to use F5. So you can see here now the build command is running, which is the pre-launch task. Okay, now the GDB server starts up. So you can see here it starts up the J-Link GDB server for us, targeting an NRF, target interface is SWD. Okay, it's resetting the target and we are debugging. All right, we can step over. Okay, let's get the board showing. Okay, so you can see here the board is not currently doing anything. Pin is configured. Okay, so the pin automatically went high. So if we run this toggle DT LED now, it should turn the LED off. The LED is off. We can place a breakpoint over here and we can say run, and it should be around 1 second. LED is off, it should go on again. LED is on again, LED stays on, which is important, and great stuff. We are debugging. On the side here is your variables, your watch lists, you can add whatever. Now you got an option, either stop. The default is to disconnect and suspend. I just want to I actually want to have this running again, that it runs itself. I want to remove that breakpoint, but continue running. Let's see. Yes, indeed, it does still blink. So we want to just disconnect. Otherwise, it's going to disconnect and suspend. And disconnect and suspend stops the CPU. I want to have the CPU to continue running. Okay. So you can see it still runs over there. Okay, so we have one more item left, and that will be the device tree overlay. Now, what we want to do is add a file, which is app.overlay, which is the default overlay file. So an overlay file, you start with /brace and then comma point. This is a language on its own. You will need to learn it if you want to have any proficiency whatsoever with Zephyr. Then I want to open a file. So the file that I'm going to want to open is the device tree file for the current board. So we go to our Zephyr project in our home folder, we go to Zephyr, we go to boards, we go to Nordic over here, and then the NRF52833DK, and then we want the DTS file for that, for our particular one. So it's going to be this one, 52833DK, NRF52833.DTS. We just want to open it, and then we want to put it on the side. You can see I have a similar syntax here. So what the device tree actually is a hardware description language. So it's similar to VDHL. So this is the hardware description. What we are going to do is we are going to change the LEDs. So this is referred to as a device tree overlay. You can either override values or you can add values to a device tree. So here is the entire device tree. We are just going to change the LED values. Right, so there's a secondary file in your build files. Go into Zephyr and then you'll see a Zephyr.dts. So this is the final device tree that is compiled at the end of the day. So you can see here your SoC, your Nordic, yada yada yada. This deserves a video on its own just to explain the syntax and how the hell this works. But anyways, we want to find FLED. We want to find LED 0 because we're going to change LED 0. Okay, you can see here LED 0 is 0D, right? Now we go back to our main DTS file. We want to find that same LED 0, not PWM LED, not that one, not this one. Okay, we got these LEDs then. Then we just want to copy this small section and then paste that in. Let's just format this nicely. It won't fight me on it. Shift tab, format that in. So GPIO 13. So this is currently what it's set as. Okay, so 13 translates to D. What I'm going to do is I'm going to change this from port 0 pin 13 to port 0 pin 14. So effectively what we're going to have is LED 1 and 0 are going to be mapped to the same location. So that's the device tree currently. Well, the device tree overlay, we can close that down. Now in our build script, we want to add another part to it. So this will be another -D, and this will be DTC underscore overlay, and then underscore file, and equals to, okay, and that will be to the app overlay file. So app.overlay. Okay, so the file name doesn't really matter, but this is the default to call it app.overlay. Now the next thing we want to do is we want to build again. Let's just double check. So we have changed it to GPIO 14. So I'm just going to keep it highlighted over here. This is the final device tree output. So you can see this is D, which is equivalent to 13 currently. Okay, so let's do a build. So F1, run task, run the build task. Okay, so apparently this failed. Oh, this needs to be encapsulated in LEDs. Okay, so we needed to add this LED tag above it, or node. I believe they call it nodes. F1, then we run the task again, we say build. So what you're looking for is this found device tree overlay, and then the app as well. And then you can see also here, it is already constructed the new device tree. So this changed from D to E. Okay, we're done building. So what you should see now is that the LED is going to change on the DK when I run the debugger. We're running debugger now. So we just put a breakpoint over here. You should see the one LED light up and it appears. And now again, if I want to change anything here, we just go to our app overlay. You can actually close this one now. It's not that important. And make this 15. This will now be LED 2, I believe. So LED 0 and LED 2 will have the same alias effectively. Okay, debugging has started. Okay, so we should see the LED change again. Okay, so there's the LED. Okay, so that's a basic introduction to getting Zephyr up and going with a Nordic DK. A like, share, comment and subscribe is always appreciated. Thank you. Have a nice day.